Good morning, ladies and gentlemen. In today's episode, we'll be continuing our look at related rates. Before we get into our first related rates problem, though, I want to look at a few more trigonometric derivatives. We've seen that the derivative of sine is cosine and the derivative of cosine is negative sine. You also need to know that the derivative of tangent is secant squared x, and the derivative of secant is secant tangent. The derivative of cosecant is negative cosecant cotangent, and the derivative of cotangent is negative cosecant squared. In our first related rates problem today, we have a camera on the ground 3,000 meters from a rocket's launch pad. The camera is designed to rotate to stay aimed at the rocket. If the rocket is rising at 800 meters per second, how fast is the angle of elevation of the camera changing when the rocket is 4,000 meters above the ground? First, we will make a sketch. Here's a sketch of our problem. We have a camera 3,000 meters from the rocket launch pad, and we have a rocket rising at a rate of 800 meters per second and reaching 4,000 meters, at which point we need to know the angle of elevation, and I'm going to represent that with the variable theta. Now in step 2, let's list our variables. So we have theta, we have x equal to 3,000, we have y equal to 4,000. We have y prime, dy dt, the rate of change of the rocket with respect to time, and that's going to be 800. In this next step, step 3, we have to come up with an equation. So using our right triangle trigonometry, we could come up with a few equations. So consider the following. We could do sine of theta is y over h. We'll call this h. And using the Pythagorean theorem, this is 5,000 at the time that y is 4,000. So we might be able to do something with that. Cosine theta, we could say is equal to x over h. Now that's intriguing because x is a constant. It's not changing. The camera is always 3,000 meters away from the rocket launch pad. Another that we might consider would be tangent of theta, and that's going to be y over x. Now we get to use our constant variable, the x. But notice we also are going to come up with, when we differentiate this, with a y prime. And we know y prime. So this might be our best choice. And we'll go with this equation. And we'll plug in our constant variable. Tangent of theta is going to be y over x, which is 3,000. X is a constant in this problem. Next, we'll differentiate our equation. Tangent, the derivative of tangent is secant squared theta times theta prime. And we're differentiating with respect to time, so we're using the chain rule. That's d theta dt. And now this is 1 over 3,000 y times y prime, the derivative of y with respect to t. In step 6, we'll plug in our variables. Now we have secant squared theta. Well, we have a right triangle over here, and we know that cosine of theta is at the point in time when the rocket is 4,000 meters in the air is equal to 3,000 over 5,000, or 3/5. So secant is going to be 5/3 squared times theta prime, and it's going to be 1 over 3,000 times y prime, which is 800. Finally, I will solve for theta prime, and that's going to be 0.096. And that is the rate of change of the angle of elevation. So what would the units be? What would an angle of elevation's units be per second? Well, that's going to be radians per second. In our next problem, we have water draining from a conical tank at 3 meters cubed per minute. The tank is 15 meters high with a radius of 5 meters. How fast is the water level changing when the water level is 10 meters high? Well, first let's draw a picture. And here is our conical tank, and it has a radius of 5. It has a height, the tank has a height of 15. And we're interested in what's happening when the water level is at 10 feet. So when the water here is 10 feet deep. So now let's list our variables. We are interested in this problem in the cone formed by the water. So the water's height that we're interested in is 10. We don't know the radius right now. We do know that the rate of change of the volume is -3. So dV dt is -3. Next, let's find an equation. Well, the equation for a cone, cone's volume is 1/3 pi r squared times h. Now, before we differentiate, let's look at our equation, the variables in it, and what's going to happen when we differentiate this equation. So V, the volume, is going to become V prime. And we know that the change in volume is -3. So that's going to work out well. Then it's going to be 1/3 pi, and then we have a product rule here where the result's going to have both r and h and r prime and h prime. Now, h and h prime are not a problem. We have h and we're looking for h prime, but r and r prime we don't know a whole lot about. So there's a way to get around this where we can define r in terms of h before we differentiate. So let's see how we're going to do that. Now notice in our picture here we have similar triangles. So I'll try to sketch them here. So one formed by the radius and height of the water cone. So that's h equals 10, and this is our r. And the other formed by the radius and height of the tank itself. So those two triangles are similar, and we can write the radius and the height, radius over height of the tank is always going to be equal to the radius over the height of the water triangle. Now we solve for r in terms of h, and we get that r equals h over 3. Now we can, and that's always true, that's a constant. R is always equal to h over 3 as the cone of water is decreasing. So now we can plug that into r in our equation. And simplify that before we differentiate. Now that's going to be a much easier equation to differentiate. So next we're going to plug in our constant variables. We don't have any because the volume is changing and the height of the water cone is changing. So we will differentiate. So that's going to be V prime dV dt, the change in volume with respect to time. This is going to be pi over 27 times 3 h squared times h prime. And v prime simplifies to pi over 9 h squared times h prime. Now we will plug in the rest of the variables. So v prime is -3. And that's pi over 9. H is 10 squared times h prime, which is what we're looking for. So that's our single variable, and that's the way it should be, because we're looking for how fast the water level is changing when the water level is 10 feet high. So h prime turns out to be -0.859, and what are the units going to be on that? Well, this is h prime, or the change in height with respect to time. Height is measured in meters, and our unit of time is going to be seconds, minutes. And one last thing, I want to point out that the sign of h prime is negative. The interpretation of this is that the height of the water level is decreasing at a rate of positive 0.859 meters per minute. So the decreasing here, that word can take the place of the negative sign. This next one's a fun problem where I think the key to the problem is making a good sketch of the situation. So we have a 6-foot tall man walking at a rate of 5 feet per second away from a light pole that is 15 feet high. When he is 10 feet away, how fast is the tip of his shadow moving? Well, first let's make that sketch. So here's my sketch, and we can see we have a light pole that's 15 feet tall. We have a 6-foot tall person walking away from the light pole. Now notice in my sketch I've defined variables for the distance from the light pole, so that's going to be a changing variable. And I defined another variable, s, for the length of the shadow, which is also going to be changing as he's walking away. So it's very important to define anything that's changing in your picture as a variable. Now we also know that x prime is equal to 5 feet per second. That's the rate of change of the person from the light pole. So we have our variables defined and we have our sketch. So what is the equation that we're going to use for this problem? Well, if you notice, there are similar triangles in this problem. So we have a triangle there, and we have this triangle. And those are similar triangles. They both have a 90-degree angle, and they share an angle. So we can set up a similar triangle equation. We can say that 15 over x plus s, 15 over x plus s equals 6 over s. So take a look at that equation and make sure you can see the similar triangles. 15 over x plus s is going to be the same as 6 over s. Now we can simplify that. Let's go ahead and simplify that before we differentiate. 15s equals 6 times x plus s. Now in step 4, we plug in constant variables, and you can see that s is changing, the length of the shadow is changing, the length of the distance from the person to the light pole is also changing. So there's nothing to plug in. Next we will differentiate this equation with respect to time. So let's differentiate. So we have 15s, that's going to be 15s prime, equals 6 times the derivative of x plus s with respect to time. Well, that's going to be dx dt plus ds dt, or x prime plus s prime. Next, we'll plug in the rest of our variables and solve. So we're at step 6 now. And that's going to be 15 s prime equals 6 times, well, x prime is 5 feet per second. That's the speed that the person's walking away from the light pole. So that's going to be 5 plus s prime. So next we're going to solve for s prime. That's the only variable left. And if you go back to the problem, we're asking how fast is the tip of the shadow moving? Well, that's going to be the rate of change of s. So let's solve for s prime. And s prime comes out to be 10/3. So next and the last step is to label with correct units. So 10/3 what? Well, it's the rate that the length is changing. So that's going to be feet per second. Our unit is feet, and our unit of time is seconds.